Hey, hey. Well, I think I've started finally. And we'll get rid of all that. Okay, let's make sure. Am I going now? Am I good? Yes. Okay. Wow. I did like 6 minutes of the stream without you guys, so I guess I'm practiced up. All right. Thanks for saying something. Please always do that. I don't know. Well, I thought I clicked something, but it didn't. So I humbly apologize. I appreciate your patience. No wonder somebody was falling asleep. Great. All right. Yeah, I try. I try. Okay. So I'm going to try to remember what I've been saying for the last 6 minutes. I'm going to start from the beginning, though, of course, because nobody else heard me except for maybe my dog. We got our test on Wednesday, and we don't have school on Tuesday because it's election day, which is good. Mr. Kelly's going to review with you tomorrow. I'm not sure exactly what he's got planned. I'm sure it's amazing things, hopefully helpful. But this will hopefully help you as well. I'm going to try to keep it as short as possible. It won't be anywhere near as long as last time, I think. But we will see. I'll answer any and all questions that you might have. All right. So like it says too on the screen here, but stay engaged here. You guys were like, I was like, why is somebody put a sleepy thing on there? Because like, what the heck? Now I understand. But try to stay engaged, like down here, be ready to take some notes, right? So write some stuff down and take notes, be engaged. You can put answers in the thingy if you want to. It doesn't, but something just so this is not just like background. Because if it's background, you might pick something up just accidentally. But if you could stay focused and pay attention the whole time, it's going to be way more helpful and it's going to be not wasting your time. All right. So if you got other things going on, maybe just set those aside for just a little while. All right. And like it says here, you can use the chat like, ooh, hello. No, let's not end anything. As I saw in the, this is why I knew you guys weren't seeing me because I was looking at the chat. And I see a remind. Let's see. Okay, cool. So somebody said something to remind, and I just saw that too. So I think we're good. All right. All right. We're good now. Nope. Wait. Nope. Yeah. Okay, now I can see. Okay, I think we're good. All right. I don't live stream very much. Last time I did it was last time we did a test. All right. Maybe I should live stream something else. But maybe not. All right. So let's start get into this because this is a test, right? We're not going to talk about live streaming games or anything like that. We're going to live stream physics because that's what we're all here for. So inertia and free body diagrams. This question is asking us to rank these from least to most inertia. And if you cast your mind back to, I don't even know when you first started learning this stuff, and you probably have heard the word inertia for like a long time ago too. Inertia, to answer this question, just remember there's only one thing, one quality of an object that affects the inertia. Just one. And if you can remember what that one thing is, that's going to help you with this type of question. And so basically that one thing is the mass. All right. The mass is the only thing that affects inertia. That's it. Not the speed, nothing else. Okay. So if you replace the question, if you replace the word inertia in the question with the word mass, that makes this a whole lot easier. Okay. So literally to go from least to most inertia, the least to most mass. That's it. So a small cat running at the top speed is going to be our number one least amount of inertia because even though it's running at top speed, the mass is all that matters for inertia. The dog at rest. You're getting it. Yep. And honestly, since the first time I said this tonight, I paused and I said, make sure you get this in your head. I mean, right now you got this now, right? Yeah, you've got it. Well, you're mostly correct there. Yeah, so the city-sized asteroid is going to be, a fully loaded truck is going to be smaller than an asteroid. So even though the asteroid is sitting there motionless in space, it's got a tremendous amount of mass. And there's no friction, there's no gravity, whatever. But to get that asteroid to start to move would take a tremendous amount of force because it has a lot of inertia. It's trying to just sit there. Not trying, but that's the analogy we use. More mass just means more inertia. If that asteroid was moving, it would take a tremendous amount of energy, or force, I should say, a tremendous amount of force to stop it or to slow it down or to change its direction or whatever. So more mass is the point, means more inertia. That's it. Mass and inertia. That's it. So remember, nothing else. So hopefully maybe you're writing something down. Mass is inertia. Inertia is mass. I shouldn't say is. It's not the exact same thing, but the only thing that affects the amount of inertia something has is its mass. All right. Stop me if you got any questions. Okay. Free body diagrams is what this next part is going to be about. The test is on Wednesday. It's going to be mostly multiple choice, but also some free response. And you might have to draw a free body diagram. All right. Just be ready for that. Fortunately, it's not too tough. And I'm going to give you some hints and tips for this. We got the forces acting on an apple hanging from a tree. The trick for drawing a free body diagram is to just focus on the subject of the sentence, the what we call the object. Okay, we got an apple hanging from a tree. You might be able to draw an apple because it's not that tough, but it doesn't matter what it is. It's the object. It's the focus of our little statement here. And we always represent these objects in physics with a square. Okay, you can do it with a circle, but I mean, that's also, but I'm just telling you, just we'll all be consistent and do a square. If some other physics teacher in the future says circle, it goes either way. An object, the point is you don't have to draw an apple. Keep it nice and simple. And then forget about everything else. You don't have to draw it. You don't have to draw the stem. You don't have to draw a tree. You don't have to worry about like equal and opposite at this point. You're drawing the forces acting on the apple. So what forces are acting on the apple? And I always start with the question, is there gravity? And if it's on Earth, the answer is yes. So gravity is always going to pull straight down. So it would have force tension too also. But like I said, I kind of get in the habit of just like trying to find like ways of like a path to follow for these types of things. And you're right, it is going to have tension, but I like just to kind of make it consistent and just make sure I don't forget anything. I like to start, you do how you do, but I know gravity is going to be there unless it's floating out in space. And so I draw a little arrow pointing down and I label FG or F gravity or something to indicate the force of gravity pulling downward. And then getting to that tension force of tension, I ask myself, is there something balancing out gravity? And a lot of times, if the apple was like sitting on the table, then yeah, the table will be, that's our normal force. So that's something worth mentioning. Maybe I'll mention that in a minute. But in this case, you're right. Why am I talking about it? It's not too hard, right? I'm overcomplicating it. But I really just want to make sure you see the thought process behind this. It's pretty simple, but it's also easy to get like start second guessing yourself. And start overthinking it. Like, what about the tree? What about this? Like, what about the air? Just what's acting on the apple, and that's it. Force of tension pulling upward, and the arrows are like the same size because the forces are balanced. They're canceling each other out. The apple is just sitting there. All right. If you want to pop a question in either the chat, I'm looking at it. I also have my phone off to the side here with the Remind app up. Let me know. I will go back if I need to. All right. There's there's usually a delay when I live stream, like 15 seconds. So I might not see your question right away. That's fine. So I will see it. I just might have to go back to it. All right. We got a car moving at a steady 50 miles an hour. Again, you might be tempted to draw it looking like a car. You might be tempted to draw the road. Don't. Just focus on the object, basically the subject of the sentence. What does the object look like? Well, in physics, we're going to draw it looking like that, right? That's supposed to be a square, but close enough. Okay, then my thought process is there gravity? Yes, there is. Cars get pulled downward by the force of gravity. Okay, then I ask myself, is there something balancing out gravity? Yes, there is, because the car is not falling or anything like that. And it's not going up, it's not going down, it's not accelerating up or down. So the arrows are going to be balanced again. And in this case, it is what I mentioned earlier. The road is exerting a normal force. Normal is I feel like I've said this, but maybe I'll say it again because it's a review. Normal is a mathematical term. All normal means it's perpendicular. That's all normal means. It's perpendicular to a plane. So F normal. I will write the whole word out. Norm. You could usually just stop there and you'll be fine, but I'm going to continue that because the force of normal force. Then it's a car moving at steady 50 miles an hour. Now, if you know anything about cars, to go at 50 miles an hour, you're going to have to keep your foot on the gas because there's air resistance. Now, it doesn't say in friction, there's a bunch of forces. It doesn't say left or right, so I get to make that up. That's, it's kind of like, it doesn't say. It just says 50 miles an hour. Now, I drew this arrow much larger because I want to show you something. I'm going to call this you can call it the engine force, but really, I'm just going to call it applied force. Okay, applied force, because the engine is applying a force. Okay, you don't have to worry about the drivetrain or any parts of it, like how the engine applies the force. It's just applying a force. Okay. Now it's going at a steady speed, and that right there is a clue. It's not accelerating positively or negatively, which means that I'm going to try to do my very best to draw this arrow the same length as the applied force. It doesn't have to be the same as the other two because normal and gravity are the same, and they're going to cancel each other out going north and south. No, I'm sorry, up and down. Okay, good. Yes. The side-to-side forces are also going to cancel each other out, and that's fine because it's a steady pace. So yeah, we could call this one friction. There's also air resistance too if you want to add that as well, but let's just keep it kind of simple for now. As long as you got friction, friction's going to be the big one. Okay. So the takeaway here is that those are balanced, and therefore it's going to be either, let's put it this way, the velocity is going to be, because the force, no, let me put it, the velocity is not changing for both the apple and the car. The velocity, it's staying the same. There's no acceleration. Because it's steady, this one is hanging out at a steady 0 miles per hour, this apple. Okay, it's not changing its velocity. This one is hanging out at a steady 50 miles an hour, not changing its velocity. It means it's not accelerating. So the forces have to be balanced. All right. So that's kind of a clue right there. Probably guess where I'm going next. The force is acting on an apple falling from a tree. Well, if it's falling from a tree, it will be speeding up. All right. And so I'm going to draw my apple again. And I'm going to go, well, is there gravity? Yeah, there's gravity pulling it down. All right, the force of gravity. Now it's falling. Now there might be a tiny little bit of air resistance. It doesn't say to ignore air resistance, so I can't. But it's going to be like a tiny little arrow. Definitely unbalanced. All right, it's falling. It's speeding up. It's accelerating. And so this is unbalanced. Balanced. Long words. Got to focus here. It's unbalanced. These are unbalanced forces. That's the key here. It doesn't give us numbers, so I'm just going to make sure I draw my arrows very noticeably unbalanced, like that, okay? This one is down here speeding up, also unbalanced. It's accelerating to the right, speeding up to the right. So I'm going to draw my car again. I'm going to draw gravity because, like I said, I like to start with gravity. Is there something balancing out gravity? Sure there is. Whoa, but it's not gravity balancing out gravity. That's just crazy. That's called normal force again. Norm. There we go. Now it's speeding up to the right. So that is going to be our applied force again. And we're still going to have friction and all that. But the key is it's unbalanced. Okay, the car is not falling up or down. So these two are going to be balanced. Up and down are going to be balanced. It is speeding up to the right. And so since it's speeding up to the right, I know I want to make my arrow to the right longer. All right. All right. A little bit more multiple choicey. As a driver of a car oh, okay. You got to focus on this one. Read these ones carefully. These are so confusing. These can be very confusing. We have a tendency to either underthink or overthink these types of questions. So let me read it. As a driver of a car turns left at a steady speed, they hear their phone on the roof sliding to the right. Which diagram represents the forces acting on the phone? Now, there's only going to be one answer. You don't have to put it in chat if you don't want to. But make up your mind. What would you choose? Okay. It says the phone is sliding to the right. And so, thank you. Cryonic Dew 24. I appreciate you putting that on there because that is the most. So the problem is that's not it. And it's not going to be D either. Now, I appreciate what you're thinking. So I'm going to take a guess as to what you're thinking. Is that this over here, this little arrow over to the left represents friction because you could hear it sliding. So there's obviously friction involved, but something is pushing the phone to the right. No, don't worry about this. This is why we got reviewed. This is why I'm reviewing, okay? So you get it wrong tonight, but when you see a question that's just like this on Wednesday's test, it won't be the same words, might not even be a cell phone. You'll get it right and you'll get it correct then because you saw it. I'm going to explain this one, all right? So immediately what you're going to do on Wednesday's test is you're going to say, wait a minute, I remember this. Something just like this. Okay, so it's not those. Okay, we could also eliminate A because you know something's going on. I don't know what's going on with that one. Let's see. This one, we'll eliminate some of these obvious ones, right? There's no forces to the side. Okay, so I eliminated the ones that, so this is what you can do to yourself. So that leaves us, well, of the non-obvious choices is E, I, and J, right? Now it's accelerating, it's sliding to the right. So we could probably eliminate J because these are too balanced. And if that was the case, the phone probably shouldn't be sliding one way or the other. So that leaves us with like two that don't make sense. But okay, here's what we got to do. Remember what I said earlier about drawing force diagrams? Remember what we said earlier about drawing force diagrams? I know, right? Focus on the object, okay? In this case, focus on what was the object? The object is not the driver. The object is the forces acting on the phone. So the object is the phone. Focus on that only, okay? Now, when you're in the car and you hear it sliding to the left, that's not what's happening. You're not, be the phone, okay? Be the phone. Just put yourself, you are the phone, you're riding on top of the car, and some idiot, usually me, puts this, hey, by the way, life pro tip, do not just get in the habit of never putting anything on top of the car. Never put anything on top of a car, because, anyway, you are the phone. I'm getting, you are the phone, right? The driver was going straight, and all of a sudden the driver turns to the left. What are you gonna do? You're going to try to keep going straight as the phone. But what's going to happen is there's going to be a little bit of friction pulling you to the left with the car, but you're still, it's just not enough. It's not enough to turn, like you're still going to slide because you're trying to go straight and the car is turning out from underneath you. All right. The only force acting on you, well, besides gravity and all that, the only force acting on you besides gravity and normal is the frictional force of the car turning to the left. So you're going to try to go straight. You're going to get pulled to the left a little bit, but not as much as the car. So you are the phone. Put yourself in the place of the object that's in a question like this, and that helps you figure out what's going on. All right. Tough one because right. All right, be the phone. That's my tip for you tonight. Be the phone. All right, if you got questions about that more, you can come back. We can come back. But yeah, right. All right, here's another one. These are tough. Multiple choice. Which of these? Okay, so this kind of implies that there's gonna be more than one. So I'll give you a hint. There could be more than one answer here. Could be moving to the left. Which of these could be moving to the left? Moving, not accelerating. Moving to the left. And you're going to hate me after this one. Well, you're partly right. You ready? Here's the answer. All of them could be moving to the left. You're all partly right. It could be E, it could be J, it could be all. All of them could be moving to the left. Right. I know. This is why we're reviewing. Moving is not accelerating. Okay. Acceleration. You're looking at the arrows. Okay. Here, let me put it this way. These are free body diagrams, force body diagrams. What do unbalanced forces cause? An unbalanced forces causes an acceleration. An acceleration is a change in movement. Okay. So an unbalanced force causes a change. Keyword change in motion. I'll say it again. An unbalanced force causes a change in motion. Okay. A does not have an unbalanced force. It could be moving to the left and it's not going to change. B has an unbalanced force. It could be moving to the left, but it's going to start to slow down because something is pushing it to the right. C could be moving to the left, but now it's going to also start to move downward. D could be moving to the left, but like B, it's going to be starting to slow down and maybe eventually move to the right. E could be moving to the left, could be moving to the left, and since the arrow is pointing to the left, it's going to start to speed up. F could be moving to the left, and it's going to continue to do so, but it's also going to start to move up, accelerate upward. It's going to start changing its motion in that direction. G could be moving to the left, but now it's also going to start to change. It's also going to start to move downward. Okay, you get the idea. H could be moved. Okay, and so I know. Don't you feel you're like, I'm so unprepared for this test? Good news. The test is Wednesday. Today is Sunday, and you're watching this and you are learning. All right. These forces. So arrows. Here, I'm going to write this down. Arrows. I might have. Okay. Arrows are forces. They represent forces. Force. Unbalanced. Forces. Change. I'm going to use the fancy Greek letter there. Change motion. Motion. Maybe I should not be writing all this. Motion. Okay. I guess that's all I was going to write. Arrows are represent forces, and the forces change motion. They change motion. Okay, that little fancy symbol there is change. I guess I could write change. Okay. They change motion. All right. Ready? So in contrast to this question, which of these could be accelerating to the left? Okay, the previous question was which one could be moving to the left. Now, which one or ones, which of these, I'll tell you, there's more than one answer. Which of these could be accelerating to the left? You could put your answer in the chat. You could just think it, because now you might be getting scared to put stuff in the chat, but don't. I mean, you putting stuff in the chat is awesome because it gives me a little idea like where you're at with this stuff. And it tells me that this is a good thing we're talking about this. Okay, there's two choices. One of them is E. And the other one, if you got it, you got it, is I. Okay, in fact, it's accelerating, and it's not even could be. It's like is accelerating to the left. It's like it's not just could be, it actually is. And why? Because of those unbalanced forces. I could draw arrows, I think. That's why it's accelerating to the left. And what did I say in the previous one? Those arrows represent forces, and unbalanced forces causes a change in motion. What's acceleration? Acceleration is change in motion. Good thing we're reviewing. Right? You thought you just had questions on the review guide. All right, pop those questions in the chat if you have any. I will get to them if you have any. Which of these could be at rest? There's more than one. And it is a could be. It's not is. Okay, so could be at rest. It might not be. It might not be. It might be moving. but it could be at rest. More than one answer. A is one of them. Yes. J is one of them. Very good. One more. No, you're right. Nice job. Which other one could be at rest? Let me see the pattern here. The pattern, it is H. Good. The pattern here, okay. One little trick that might help you is when you see the word at rest, just think of that as its velocity is 0. Okay, it's just another velocity. Okay, it could be going at 10 miles an hour. It could be going at 100 miles an hour. It could be going at 0.5 miles an hour or meters per second or whatever. It could be going at 0. And if you think about at rest as just another velocity, that makes like A, who knows what A is doing, but it's definitely not changing its velocity. Same thing with H and J. It's not changing its velocity, whatever it might be. It might be at rest. Might not be. Nice job. Draw the forces acting on a 300 Newton object sitting at rest on a 20-degree ramp. Okay, so Mr. Kelly, I know just got done doing this. I'm being kind of unspecific here with the object. So a 20-degree ramp. We got basically, I'm going to draw like a little sketch, just a ramp, and we basically got that. And here's our theta, 20 degrees, right? Okay. How do we start? Well, like with a lot of these things, start with gravity. All right. And what I'm going to do is I'm going to sort of, no, I'm not. I'm going to draw it like at an angle again, just to kind of get rid of that ramp a bit, because it gets a little clutterfied. And we need to, like, my pen is not, I have terrible handwriting. You probably have noticed that. So what I'm going to do is I'm going to draw it like from the middle of the square. Usually you don't start from the middle of the square. Excuse me. But I'm going to, and I'm going to draw this a nice big FG. Okay. Now let's just sketch this because we know what we got. We got gravity pulling down, and we're going to have some sort of normal force. Like we're going to have, we don't know what it is. I'm just kind of sketching it, right? So those are the only two forces acting on this. That's it. Gravity and normal force. And they're at some angle and they're at some length, and we don't know what it is. So this is just a sketch. So sketch. Okay. Just to kind of give us an idea where we're heading. Okay. And start with gravity. So then all you got to do is this. No, I'm not going to change color. I'll just leave it at this. You know what? No, I'm going to change color because I got like too many things going on over here. All right, let's go with this light blue. No, we won't be able to see light blue. Mr. Chern, what are you thinking? Let's try that again. We'll go with deep red. All right, because here's what you got to do. You got to remember, perpendicular and parallel. What are the perpendicular and parallel components working on this? And so here's what I do. I kind of like envision a right triangle. Like this, the FG is my hypotenuse of all my triangles. And so I need to envision a right triangle. And so what I'm going to do is I'm going to draw a line, just kind of lightly sketch it, parallel to the force of gravity here. Or I'm sorry, parallel to the ramp. Parallel to the ramp. Okay, so there's my parallel to the ramp. I'm going to draw another one. I'm going to kind of eyeball this. This is a little bit more tricky here. I want to basically intersect from that line. I want to draw perpendicular to the ramp. Okay. And I'm going to try to eyeball it, making this my 90-degree angle. And I'm going to draw it so it reaches my arrowhead. And what some people do is maybe if I didn't quite make that, I will readjust my arrowhead a little bit. I could draw that a little, if you just draw everything really lightly in pencil, you can make your changes. And so here I have my 90-degree angle because perpendicular and parallel always are 90 degrees to each other. And what I can do then is I can go through and I can just erase the little mess I might have made. And now I kind of have a sketch of that's going to inform me as to my components. And what that's kind of telling me is, where'd my little pen go? There you are. Is, I think you can see this, right? Gravity is pulling down the ramp this much. Okay. We're not going to worry about that. But like gravity's kind of doing two jobs right now because it's a tilted ramp. I mean, as you know, if you ever tilt anything, gravity does two things. gravity holds it to the ramp, and gravity also pulls it down the ramp. And so that's what these two little legs of the triangle represent. The shorter one represents, oh, there's actually another force. There's another force I forgot. We'll get to that. And good thing we're doing this. So gravity is pulling it down the ramp with this much force. This is going to be our F parallel. And then gravity is also pulling into the ramp this much. That's our F perpendicular. Okay. And remember the question I asked earlier, what forces are balancing out gravity? There's two. I only included one here. I only included normal. There's another one. There's another force. So let's start with that one. Now, normal force acts perpendicular to the surface. So what I'm going to do is perpendicular, the normal force is going to be the exact, it's going to balance this out. It's just sitting there. Everything's at rest. And so I'm going to try my best to draw an arrow that is like this. And just to use the mathematical term, I'm going to try to make those two the same size. All right. And this is going to be my normal force. My normal force. And it's going to be the same size as the perpendicular force. The force I forgot to mention is the thing that's actually holding on to the ramp is the force of friction. So I'm going to do like, I don't know, friction is like doing this. Friction. So now I know exactly how hard friction is pulling. It's going to be the same length as this line right there, that leg. So I'm going to do my best to draw that F friction. Then what I'm going to do, I'm going to leave them here, erase. Did I spell, why can't I spell? I'll have to start over. Erase, I knew the A just kind of snuck in there. Erase the red stuff. Erase the components, okay? Because those don't belong. Those don't actually exist. Those are just helping. Those are a figment of our imagination. They're just there to help us visualize everything else. So once we erase that, we'll have our free body diagram. When can we install friction? You got it. I mean, you asked the question that I forgot about at the beginning. So you got it. Good question. All right. So there you go. Just like that. So draw the triangle with like the very lightly. Oh, sorry. So I'll just draw FG. Draw the we'll do parallel and perpendicular lightly. Everything's lightly, right? Because you might need to change things. And then draw normal and friction. Okay, so those are our basics. Oh, and then erase perpendicular and parallel, the components. All right, that's it. Draw and label them as well. Good. All right, last one for inertia. What is always true? Now, whenever you see the word always on a test, that's like alarm bells should be silently going off in your head, right? Because it's like, wait a minute, always. Okay, always is like that, like red flag. So what is always true about the forces acting on an object that is moving at a constant speed? If you've been paying attention, you know what the answer is here. Right? What's always true? Always true. A. Yeah. Whoop. That's it. Always true. It could be that there's no forces acting on it. You know, I don't know how to draw somebody shrugging, but it could be. But there is a net force. Definitely not C and definitely not D though. All right. Very good. So they're balanced. Balanced forces means constant speed because an unbalanced force causes an acceleration, and an acceleration means a changing velocity, changing motion. Would the answer apply to an object at rest? Yes, because an object at rest. All right, what's going on, Mr. Jaron? At rest is a velocity. It's just a velocity of 0. So like I said, if you think of at rest as a velocity of 0, then yes, it definitely could be considered it would still apply. Okay. That's the clock from stream. Are there any questions about unit 2.1? Yeah, good, good. If you do have questions, pop them in the chat. I'll answer them, but I'd like to move on because I started late and I like to talk, so we're going. I hope things work. Let's see. Okay, good. All right, which of these are vectors? Oh, this is nice and easy, right? Okay. In your head, you got the answer? So is velocity a vector? Yes. Is speed a vector? No. Is force a vector? I've been a streamer for a while. Acceleration a vector? Yes, because it's a changing velocity. 10 meters per second. No. I'll answer this question first. East. Okay, as soon as you see the word direction, as soon as you see a direction, yes, that is a vector. No, there's no direction here. Up, there is a direction, so H is a vector. So vectors are mud. What somebody told me a long time ago, one of my students made this up. Magnitude, that's the number. Unit, and direction. So if you got those three things, you're a vector. No, I used to, when I first started streaming this, I did stream on Twitch, and I do have an account there, but more people have access to and know what YouTube is than know or have like a Twitch account. So I switched to YouTube to stream for physics. I tried. Have I streamed gaming? No. Well, it's not my favorite thing to do. But we're wasting time here. Yeah, no, streaming. Well, let's just say when I play video games, it's not like a community event for me. Minecraft education. During lockdown, I actually did rent a. During COVID, I rented a server I did the Legends thing, and I invited my classes to play, and we played like a bunch of stuff. It was pretty fun. I know these are important questions, so I'm going to take like 30 seconds and answer them. It's fine. Yeah, no. So that was one of the when we did that lockdown in the spring, and everybody had to go home for spring break and never come back. I'm like, let's play Minecraft. We did. But that's not my usual. I mean, Call of Duty. All right, let's get back to physics. What is a net force if we got 30 newtons west and 10 newtons to the east? Well, okay, you're gonna have this. Never eat soggy waffles. This will be here. Look, in fact, I could show you. Whoop, there we go. Hit the wrong button on OBS. Now I hit the wrong button. I'm all okay. So anyway, this is on your where we go. Why can't I screw? Well, you can see it. You can see part of it anyway. The compass rose will be on your equation sheet. You'll have access to that. All right. So you won't ever have to actually like, draw it like I just did. But since I don't have it up, here we go. Never eat soggy waffles. So this is nice and simple. All right. If you remember, north is positive, east is positive, south is negative, and west is negative. That's basically the best way. So basically west is going to be negative and this 10 is going to be positive because it's east. When you want net force, you just take the sum in this case. Okay. In this case, because they're vectors. So, we get into weird angle stuff later on. But if you can, just add them up. So we end up a negative 30 and a positive 10 leaves us with a negative 20. And because we said negative represents west, we can just say our final answer is 20 newtons to the west. All right. So you don't have to put negative because negative means west. It's a way of mathematically indicating the direction. All right. This one's slightly more complicated. Once again, never eat waffles unless it's dripping with maple syrup and butter. In that case, you should go nuts if you like them, or if you don't, just try it. All right, this is not the same. We've got a Yeah, positive and negative, they're both positive, but that doesn't help us here. The negative positive things only helps like with a number line. I mean, number lines go, you know, from negative to positive and zeros in the middle. It's like, here's my negatives, here's my positive. They had to be, you know, opposites of each other. In this case, they're not opposites of each other. They're perpendicular to each other. We got 30 newtons to the north, and we've got 10 newtons to the east. That doesn't work anymore. So what we had to do is, and I kind of drew it funny, so I'm going to redraw it. Always go tip to tail. So 30 and then 10. All right, 30 newtons and then 10 newtons. And this is the one where you got to use the Pythagorean theorem to find our net force. So literally I mean, if you want to do it from the beginning, a squared plus b squared equals c squared. That's on the equation sheet if you ever are not sure. So it doesn't matter which one is which. 30 newtons squared. I like parentheses because it keeps everything nice and bundled together. 10 newtons squared is equal to c squared. So if I pop that into my calculator, 30 squared, by the way, squared button's right there. Square root key is right above that in case you're wondering. It helps if you turn this on. I am bad with turning. All right, 30 squared plus 10 squared, 1,000. Nice. I am belaboring this. You could just do this in your calculator if you want to, but the thing is, then once you do that, you have to take the square root of it, because you got to take the square root of the thing that's being squared. So to get c, which is square root of c squared, you got to take the square root of 1,000. And I don't know if you know this or not, but I see a lot of people typing in the answer like 1,000 or whatever, but sometimes the digits are super like, there's an answer key right there. It's right above. In this, you'll usually see the bottom right hand corner. It's blue. So if you ever want to use that, I'm gonna like do it. I'm gonna second. Okay, so there's the square root. There's that, and I could type in 1,000. It's not that big of a deal. But if I hit second and then that answer key, whoop, it's gonna give me my previous answer. So if you didn't know that, you should get used to using that. It's very handy. You don't have to retype anything at all. So my answer is, oh, and by the way, that's Newton squared, because those also get squared. And then you add them together because they are like terms. So Newton squared plus Newton squared gives you that. You take the square root of that, 3.31.6 newtons. Yee, that's not our final answer. I almost forgot. It's north and east. Okay. How about if I finish the problem? All right, Pythagorean theorem. Okay, I tell you what, here's the deal with these ones. This is that weird one that takes like half a page to solve. Although if you did plenty of them, if you did enough of them, they take less and less and less time to do. It is 7:50 now though, so I'm gonna start us and then I'll tell you what. So it's like, here. A little lighter than I remember it being, but you can see it. These are the ones that, okay, now how do I put this? You may have learned, even in the time since I taught this to you, you may have learned in your math class a little bit more about trigonometry. You may not have, I don't know. These steps that I've come up with are meant for everybody, regardless of how much trigonometry you've had. They're meant to, like, okay, here we got these buttons on our calculator. I don't get into necessarily what they do and what they mean. They're buttons that are useful for solving this, right? Eventually, if you haven't yet, you're gonna find out what these mean. It has to do with triangles, trigonometry, triangle, trigonometry, right? So these steps are there for you in case you don't know the trig. You don't have to follow them, but I highly suggest you do, just especially if this is how you do it. So the thing is, it says okay, we got to resolve this is the thing where we resolve the vectors into their x and y components. See the previous notes. That's what I keep flashing up there. This is the previous notes. This is those two things that I actually taught you those couple of days when Mr. Kelly was out and stuff. So all I'm gonna do west and north. All right, so let's see, never eat soggy waffles, west and north. So this one's gonna be something like that, 30 newtons, and then I'm gonna do the whole like All right, right. And this one is north and east. So this one's going to be like that for the 10 newtons. I'm going to stop there because I could help you if you have, like this would take like 5-10 minutes and I don't really want to spend the time tonight doing that. There is a video. It's already, the link is already in the description for this live stream. The link is already there. So check that out. It's an older video of mine, so it's a little like janky, but it's fine. It's good enough. I think it could help you. If you want assistance by, you know, either me or Mr. Kelly or Mr. Kelly or me, let me know or let him know, and we can help you with this. All right. We do have some time because the test is Wednesday. There is an FRQ for this. Where'd my thing go? I will write that down. FRQ. That is your warning. You will have to do this. All right. FRQ. So be ready for that. Let's get rid of that because it's not. All right. Besides that, are there any questions? Hey, my little window went away when I was switching around. Call of Duty, waffles and microplastics. Okay, so glad I watched this. Yeah, good. I'm glad. I mean, for real. And if there's any other things that you want help with, I will help you. They're not easy. You guys are amazing. So the fact that you're learning from this is good. All right. Last one, I think this is the last. Yeah, nope, there's one more after this. Okay, we'll breeze through this one. Newton's second law. There's 25 slides. I'm on slide 17. So we're almost getting there. We're getting to the end. And this one's kind of straightforward. Greater force results in what? Acceleration. Don't overthink this. Don't honors it. You know, it's like we start, wait a minute. Is it greater? This seems like a trick question. There are some easy questions on the test. There just are, okay? They're not all meant to be difficult. Some of them really just are there to see that you got a baseline understanding of this. You gotta push harder on something, it's gonna accelerate more. I will add that this probably should say greater net force because, I mean, if you got two really strong people pulling on a rope on opposite sides, you're not gonna accelerate if they're pulling equally. So it has to be a net force, greater overall unbalanced force. But I'm starting to honors this, and let's move on. Greater mass results in what kind of acceleration? Greater mass. Again, it's common sense, but sometimes things in physics, you might think it's common sense and you're wrong. So you might, well, wait, is this one of those things like, oh no, does this go against common sense? Yeah, it's less. This one does not go against common sense. Something's heavier, something has more mass. It's going to be more difficult. It's going to have less acceleration than something that's smaller. This is why a little tiny car or a little tiny bike or motorcycle can accelerate faster, accelerate quicker than like a big truck. In a race between a car and a human will assuming they can run, a human can win against a car as long as the distance is very short. All right, like if you're going 10 feet, a human will beat a car because you have so much less mass and you can accelerate quicker than the car. All right, weight and mass. Weight is the force of gravity. All right. The force of gravity. If you didn't get that before, just remember that. I'm going to write it over here. Fg is weight. What we've been calling weight our entire life is what in physics we say, hang on, let's be a little bit more precise about what it is because we're studying this. We want to be precise in our language. We want to be careful. So what physicists do is say, wait a minute, our weight, the weight of our body is just the force of gravity pulling down on us. When we step on a scale, there's nothing more complicated going on than gravity's pulling me down. It's the force of gravity. That's all weight is. It's the force of gravity. Oop, that's an accidental line, so you can ignore that. There's a couple. So, right, oh, I see, yes. So 50 newtons Is it a force? I'm sorry, is it a weight or is it a mass? This is a weight because it's a force. Newtons is the unit of force. 50 pounds is, so newtons is the metric, pounds is the non-metric, the American weigh. 50 pounds and 50 newtons are not the same amount of weight, just be clear. But pounds is another unit of weight. Okay, just like newtons is. Kilograms, I mean, let's just be real here. This is gonna be mass. That's just amount of, that's what kilograms is. Kilograms is mass. The amount of force, oh, right there, keyword. I could just stop there, honestly. That's gonna be weight. All right, pulling on an object. This is bothering me, so go away. The amount of matter an object has, that's kind of like the definition of mass. And the thing that can change based on location, if you're on the moon or on Mars or whatever, or like whatever, then your weight will change, but your mass will not. The amount of stuff that you're made of will not change. All right. All right. I'm all like red. What's going on with my face? Okay. How much would a 0.85 kilogram ball accelerate if you hit it with a 41 Newton of force? Okay, that's pretty straightforward. I'm pretty sure this is going to be on the equation sheet. Let me just pull that one up. There it is. F equals ma. That's going to be your little buddy right now. So let me get rid of that. Oh, why are we doing the little spinny thing? All right. My computer's thinking. That's not good. If I ever drop out, just everybody like scream or something and let me know if I ever drop or freeze or whatever. Okay. Bottom line is, ooh, nice. All right. I'm just going to do it. I'm going to do the 4 steps. I'm sorry. I'm going to go quick though, because we're getting to the end. So kilograms is mass. So 0.85. Yes, I know it's like you could just pop this in the calculator, right? Of course. Force, 41 newtons. Okay, 41 newtons, that's a force. So I'm going to list that down, and it wants to know the acceleration. So F equals ma. There's 2 ways to do this, depending on which way you're taught. I'm going to really quickly do both. I'm going to do them both concurrent. No, I'm going to do one and then the other. I'm going to plug the letters in, this. I'm going to do this way, and then rearrange. Mass, we know, is 0.85 kilograms times A. All right, now I had to rearrange it and solve, so I'm going to divide both sides by 0.85 kilograms. 0.85 kilograms. It's going to cancel that out. And as somebody said, that seems pretty reasonable. I'm going to take your word for it. That actually seems very reasonable. But I'm going to round it to this just because I'm difficult like that. That's a meters per second squared. So there's my answer. The other way that I do is, did you get it wrong? No, you got me all like, all right, 41 divided by 0.85. Oh. I guess I should check my work. Thank you. All right, 48.2 meters per second squared. All right, thank you, internet stranger, whoever you may be, if you choose to be anonymous. You made a good mistake. Now here, you're gonna not like this. This is why I want you to do the 4 steps. Okay, and I'm like serious. Probably everybody here just thought I could just pop that in the calculator and get the answer. And I greatly, and I very, very much appreciate Cryonic Do 24 for putting themselves out there and putting the wrong answer out there. I'm sure you were doing it on purpose to give me an opportunity to say all this. Is by doing the steps, I learned, oh, hey, I actually need to divide, not multiply. Okay, even I got carried away, just like I might go, okay, that seems reasonable. We do the 4 steps, you're like, we should multiply or divide, not multiply. So take that as a lesson. Like, honestly, how long did it take me to do this? It took me like a minute. This is a test question. This is supposed to be an easy test question. Do yourself the huge favor and take the extra time to work it out for real. I mean, you see what happens, right? The other way I was going to show you is you could just pre-rearrange it. And so like you just divide both sides by A, you know, and then you get, by M. Holy cow. Divide both sides by you're trying to solve for A, so I'm going to divide both sides by M. I'm going to cancel that out. F divided by M gives you A, and then you can plug in the numbers and you get the same answer. All right. Yes, you do. And it's tough. I get it. I really do. Understanding the physics is one little thing you take away from this, but also how to do the physics, like how to approach this. It's physics, right? I mean, it's numbers, it's math. We all know how yeah. All right. What is the mass of a person on Earth if they have a weight of... Now here's a little trick. So what is the mass? So mass is going to be our question mark. It says they have a weight, and earlier I said, well, wait a minute, Fg is weight. So I know that weight is Fg, 650 newtons. I'm like, yes, I'm writing it down because I just reminded myself, we remembered why we write this stuff down. And it seems like there's something missing, because there is. Now here's the little thing I always like to say. I didn't get to say it this year. Maybe Mr. Kelly said it, I don't know. But if you think about weight, if there's ever weight, usually it's gonna just remember 9.8. Okay, if the question asks about weight, remember 9.8 meters per second squared, or newtons per kilogram. But remember 9.8 if it deals with weight. What is 9.8? That's a great question. Let's see. It is. There it is. It's on here twice. It's right here and right here. It's the same thing. And either way, it's going to get you the same answer. It's all right. So just remember, whenever you deal with weight, remember 9.8. All right. So we're dealing with weight. So I'm going to put G is 9.8. Now I got newtons, so I'm going to use the newtons per kilogram because why not? Okay, Fg is equal to G. Wait a minute, was there a whole like equation on there? There sure was. There it is. It's this one right here. Fg is equal to mg. So Fg is equal to mg. Fg is weight. So we're in a good situation here. I'm going to use this equation. Fg is equal to mg. Okay, there's not very many equations to use. Fortunately, 650 newtons is equal to the mass, which we don't know, times 9.8 newtons per kilogram. And if I solve for that, I gotta do, since I'm multiplying, I gotta do the opposite of multiplication, 9.8. Well, let's find out. I'm not gonna jump to conclusions this time. I don't even have the answer written down. Usually I have the answer written in my notes, but I don't. Because it's a good idea for me to walk through this anyway. Newtons are gonna cancel out. Kilograms is on the bottom of the fraction. And when something's on the bottom of the fraction, that means that it comes to the top. So 650. Wow. Full here. 650 divided by 9.8. I wonder if you multiplied to get that. I bet you multiplied. So we had to divide. And so we get the mass is equal to 66.3 kilograms. Yeah. Write it out, right? Take the extra time. Well, let's find out. Good. Yeah, if you multiply it, I bet you get there. There you go. Yeah. So that's the wrong way to do it. You should multiply. I think. I mean, I'm 99% sure. So call me out if I'm doing it wrong. Like maybe I missed something big here. The other nice thing about writing it down is not only does it help you know what to do, multiply or divide, but then if you like get an answer like this and you're like, that's not one of the choices on the test, then you could go through and you could look at the whole thing and try to figure out where you messed up. All right. So let me just, that should curve around like that. Okay. You can like look at the whole thing and see, where did I mess up? So multiple reasons to write everything down. All right. An object is accelerating at 5 meters per second squared. Oh, this one's nice. I like this one. It's because it's easy. If the force acting on the object doubles, what happens to the acceleration? Nice and straightforward, right? You can think of it mathematically if you want. You know that F equals ma. So if you double the force, and mass is going to stay the same. Yeah, mass is going to stay the same because the object didn't get any bigger. That means that something has to double. And so it doubles. So it will be 10 meters per second squared. All right. Nice and simple. Keep it simple. Sometimes it is simple. Okay. That's Newton's third law. That's Newton's second law. Let's move on to Newton's third law. Okay, this is important. So pay attention. You have a puppy. Found one of your socks and has it in his mouth. When you try to take the sock away, he pulls back. Okay, I got 2 dogs, so that's probably what inspired this. If the action force is you pulling on the sock with 100 newtons to the east, what is the reaction force? You could put it in the chat if you want to, but whatever you do, think of the answer. What would you put? And then maybe think of a backup answer. Okay. So we are all over the board. That's fantastic. That's good. That's why we're doing this review. Good, right? I know, because here's what starts to happen. We overthink it. We start to just overanalyze everything. We start to think of everything. Here's the trick. Here's the trick. Focus on the object. Focus on the object, and then focus on what is the object directly affecting. All right. In fact, it's even simpler trick than that. The trick is to switch the nouns. The trick is to switch the nouns. The action force is you. There's a noun pulling on the sock. There's the other noun with 100 newtons to the east. Switch the nouns, switch the direction. I'm going to write that down. For Newton's third law, switch the nouns and direction. That's the trick. Boom, boom. I'm gonna try to draw a star. hope I don't want to draw anything like, okay. In fact, let's just erase that. That's a terrible star. Okay, switch the nouns. So you pull on sock. Listen, just listen, hear me out on this. You gotta get really basic with this. You pull sock. Sock pulls you. That's it. No puppies, no floor. You pull sock. Sock pulls you. Done. So, no, yes, no. You pull sock. Where's you? You pull sock. Sock pulls you. So it's C. Okay. Switch the nouns. Switch the direction. Don't worry about it. You got it wrong. Tonight, Wednesday, you will get it correct. Okay? That's why I'm talking about this question. That's why I'm spending time on this question. Okay? Switch the nouns, switch the direction. If you remember that when it comes to Newton's third law, when it comes to that whole equal and opposite reaction thing, right? That's what Newton's third law is all about. For every action, there's an equal and opposite reaction. Okay, what does that mean? Like anybody knows that saying. For every action, there's an equal and opposite reaction. Okay, great. What does that mean? Switch the nouns, switch the direction. Okay. If I push on the calculator pushes on me. That's it. Okay. I punch face. Okay, punch is kind of a very specific thing. If I push on the face pushes on me. You said C or A. Yeah, you did. You exactly. You did kind of got it. It was in your mindset. You guys are so supportive of each other. I love this. You guys are great. I can't wait to get back in. I can't wait to teach you guys directly again. Okay. All right, I think I have remember this, and then we'll move on. Was there one more? One more. This is it. All right. Yeah. 50 kilogram cat pounces on its owner with that much force. What is the acceleration of the cat and the owner? Okay. So for all you cat people out there, I'm not against cats. I just don't happen to own any cats at this time. Okay, now here's the thing. Before I answer this question, let me ask you another question. You got a car, okay, and that's a terrible car. Wow, let's just finish up this atrocity, right? And the car is going, and you got a little tiny bug. Let's never draw lines on a bug again. You got a little tiny bug right there. And the bug is about to get hit by the windshield. Who hits harder, the car or the bug? And the answer is they hit with the same amount of force. Same force, okay? They hit with the same force. Just remember that. Equal and opposite. The bug hits to the left. The bug pushes to the right. The car pushes to the left with the same amount of force. But because the bug is so little, it has a little bit of mass. Because F equals ma. Okay, whatever. Am. Let's not do that. F equals ma. And we could rearrange that formula to say the acceleration is equal to the force divided by the mass. The amount of force that a bug hits a car window is tiny. The amount of force that the car window hits the bug is tiny, but it's enough force to squish the bug. It doesn't take much force to squish a bug, okay? There's not a lot of mass involved for a bug. And a small number on the bottom of a fraction means it's going to have a gigantic acceleration for the bug. The poor bug is going to get like turned inside out from the front to the back because it's accelerating so much, because it's a tiny mass. Okay? So what's different is going to be the acceleration. The car, on the other hand, is going to have a gigantic mass compared to the bug. And whenever you have a gigantic number on the bottom of a fraction, here, look at it. Watch. So like 1/2, 1/3, 1/4, right? The numbers on the bottom are getting bigger, but the number itself, the whole number, is getting smaller as I go on. Okay. Bigger number on the bottom means a smaller number overall. So the acceleration for the car is going to be small. It's barely going to notice it. You probably won't notice it unless it's like one of those big bugs that leave a giant blech all over the window and you got to clean it. Okay. So my point is this. It's the same force. So if a cat pounces on an owner with 5.5 newtons of force, that cat pushes on the owner and the owner pushes back on the cat with the same exact amount of force. Right? Which means we can figure out the acceleration for both. Because if we know the cat, Owen? What am I writing? Owner. Okay. We know the cat has a mass of 5.0 kilograms. We know the force is equal to 5.5 newtons. And we got to figure out the acceleration. We know the owner has a mass of 112 kilograms. We know that the force is also 5.5 newtons in the opposite direction, but it's the same amount. And we got to figure out the acceleration. So I don't know if I'm going to actually figure this out, but we use our equation F equals ma, and we're getting kind of late, so I'm going to not figure it out. I'm just going to assume that you could probably do this, and you would do that for both. Okay? But the trick here, the key thing I'm really pointing out here, that's supposed to be an asterisk. Come on, Mr. Chair. What did I just do? Okay. All right. The key here is, let's do this. Oh yes, the highlighter works really well on a yellow background, but this is the key, is that the force is the same. Okay. I'm highlighting that in case you can't tell. All right, look, I'm going to laser point it. Same force, same force, same force. Okay. So that gives you enough information to be able to solve this. Okay. I could go back and solve it if like somebody wants me to, I will, but I figure we've talked for like an hour now, over an hour. So now would be a good time. I'll wait a couple minutes, like a minute here, because somebody might honestly ask me a question about the review guide or any other question. So if you want to hang out for another, like literally, let's just wait a minute. And if you wanted to say something, now would be a good time to ask. If you want me to go back and do anything, re-explain it, now would be a good time. You can also ask me or Mr. Kelly in the next, well, tomorrow. Feel free to use Remind. Tomorrow, Tuesday, I'll get back to you when I can. With Remind, I'm usually pretty quick unless I'm in the middle of something. Okay? Yes. All right. Well, then, seeing none. You guys are amazing. Like, for real. The way you support each other, all this stuff, the way you are not afraid to answer questions. You're not afraid to get things wrong tonight. Awesome. I cannot wait to actually be back in the classroom in a couple weeks. So, test it on Wednesday. You guys have a wonderful, amazing after whatever time it is, 8 something. And I will see you tomorrow. Take care. Bye.